Hi guys. So this is the fifth part of my lecture, and today we are gonna be starting with a new topic. In the last part of my lecture, I had discussed with you guys. We had completed the topic called as life assurance contracts, which was chapter number one. So today I start with the other type of contracts which life assurance company issues, and these are called as life annuity contracts. Okay, so this term annuity, okay, let's start with this. You have heard this earlier in CD1, right? You have heard the term annuity, but the meaning of annuity differs from what it used to be in subject CD1. It differs a bit in subject CD5. Now these annuities have become life annuities. That is, these annuities are the same regular payments that used to happen in subject CD1, but they are dependent upon lives. Okay, so we will try to understand what that means. First of all, I would like to take the definition what a life annuity is. Okay, so I'll just take down the definition that is given in the core reading at the beginning of chapter number 2. A life annuity is a contract that provides level or variable, this is important, variable payments to a life, provided that it is alive, it is still alive at that time. Okay, so what is happening here, right? See, life annuity contract, it is a contract that provides level or variable payments to a life, right? What does this mean? So the payments can, we know that any annuity is a stream of payments, right? It is a stream of payments, either monthly or annual. There are payments happening at regular intervals of time, but here the payments can be level as well as variable. That is, the payments can increase or decrease, vary in amounts. Maybe in the first year I am paying rupees 5,000, and in the second year I'm paying rupees 10,000, and in the third year the payment can be 15,000, right? So this is an example of an increasing annuity, right? So there is an increase involved here. So the payments can be level as well as variable, and they're paid to a life provided that it is alive. So as long as the contract can be such that as long as Mr. X is alive, the insurance company will keep on paying him amounts or that start with 5,000 and keep on increasing with 5,000 pounds every term, right? So that is how such contracts work, and that is what we'll be discussing in this chapter. We'll be discussing the mathematics relating to annuity contracts. Okay, so for now, I am going to assume that the payments are level because the variable payments part, it is covered in chapter number, I think, 5 or 6 of the syllabus. So we'll get to that when we come to chapter 5 or 6. For now, our payments are level, so they're like, same payments every month or every year. So 50,000, 50,000, and 50,000. Okay, constant payments are happening here as long as Mr. X is alive. Okay, so now without further delay, I would like to discuss with you guys the types of annuity contracts that we have. Okay, so briefly they have discussed the types in the very beginning of the chapter, and I had discussed these types with you earlier too. The first type is the whole life annuity. Okay, so what a whole life annuity is, it's a contract that will pay a life constant amounts provided that it is alive. This is very similar to a whole life assurance. Okay, in a whole life assurance, what was happening was when the person dies, whenever he might die, there is no term limit on this. So whenever he might die, there was a payment, right? But in case of a whole life annuity, it is just the opposite. Okay, so if I am a person and at time zero I'm buying a whole life annuity, and as long as I survive, the insurance company, it will keep on making payments, fixed payments to me as long as I'm alive. Okay, so that is what a whole life annuity is. So I get payments as long as I'm alive, and there is no time limit on this. Okay. The second type of a contract is called as a temporary annuity. Temporary annuity. Under this contract, this is very similar to a term assurance now. See, it is a whole life annuity, just limited by a term. So, for example, there's this person that is Mr. X. He is taking a policy at time zero, and the policy is a temporary annuity of n years, right? So, if this person, if, as long as this person survives, right? He survives 1, 2, 3, 4 years. As long as this person survives, he'll keep on getting payments for a maximum of n years. Okay, so he won't get any payments after n years, and he won't get any payment after he dies, right? So the payment cease at the earlier of his death, at the earlier of his death, or n years. So the payment will cease at earlier of his death or n years. They'll continue to happen unless he dies or n years expire. Okay, the maximum term limit here is n years. The next type of contracts, the third type, is called as a deferred annuity. Now this is similar to a deferred assurance. Okay, deferred annuity. So under such a contract, see, we start at time zero, and then I'm telling this guy that you pay the premium for the annuity right now. Okay, you pay the premium, and after 10 years, right now maybe you're 50 years old, so when you're 60, I am going to pay you 5,000 pounds every year till you survive. Okay, so there is such a contract. It is deferred by 10 years and it will start 10 years later. Okay, for the first 10 years I'll be paying him nothing, and if he dies here I pay him nothing. Dead, no payment. Okay, but after the expiry of 10 years, that is at age of 60, if he survives till here, every year in which he survives, I'll be paying him 5,000 pounds. So that is the kind of contract that happens here. Okay, that was a deferred annuity, and the last one is a guaranteed annuity. Guaranteed, Guaranteed. Okay, so a guaranteed annuity is this is some sort of a new contract. This is not similar to any of the assurance contracts, so this you'll have to understand. Okay, so there's this guy, there's Mr. X, and I tell him that you'll be paid, you'll be paid regular payments, you'll be paid regular payments till you survive, but guaranteed for at least 5 years. So what is happening here? See, the guaranteed period is 5 years. Okay. So what is happening here is that if Mr. X dies anytime here, okay, if he dies, if I'm making, let's say I'm making regular payments of 5,000 pounds per annum to him at the end of every year. So when he survives, he'll be getting these payments. Okay, but even if he dies before 5 years, before the expiry of 5 years, he still has guaranteed payments for 5 years. So if he dies here, he still gets his five payments at time 1, 2, 3, 4, and 5. So he has a guaranteed of getting these five payments, and after that he gets payments as long as he survives. So even if he dies here, if he dies in year 2, he will be getting all these payments, the first 5 payments, because they are guaranteed payments. They are not dependent, they're not contingent on him living or dying. Okay, but from the sixth payment onwards, this becomes similar to a whole life annuity. That is, payments are only made if he survives. So if he dies here in the sixth year, if he dies here, there'll be no payment, no payment at time 7, no payment, right? No payment at time 7. So that is how such a contract works, and we will be learning the mathematics of these things from here on. Okay, so I'll be discussing that. Okay, so the first type of contract that we are going to talk about is a whole life annuity payable in arrear. It is also called as an immediate annuity payable in arrear. So as the name suggests, this is a very simple contract. There is a contract that if a person buys this policy at time 0 at the age of X, he will be getting payments in arrears that is at the end of the periods till he survives, right? So if he survives the first year, he will get a payment at time 1. If he survives the second year, he'll get another payment at time 2. If he survives through the third year, then he gets another payment at time 3. Okay. So this is the contract, and that is what it is. Okay. And the reason this is called as an immediate annuity is to compare it against the deferred annuity, right? So as this starts immediately, it is not a deferred annuity. It is called as an immediate annuity. So the first thing we want to understand about this is the present value random variable, obviously, like all the other contracts. So the present value of random variable of this contract is basically, let's say, if this person dies at this time, we'll be expressing this present value random variable in terms of the random variable that is kx, curate lifetime random variable, because obviously discrete payments are being paid here and the payments are not continuous, so we'll be using kx and not tx like we did in the last chapter. So let's try to understand this. Okay, so if this person he dies here at, let's say, time 2.5, right? If he dies here, uh, there would have been two payments to him at time 1 and at time 2. For example, if he dies here at time, let's say, 3.6 years, there would have been three payments to him at time 1, 2, and 3, right? So there are payments in arrears happening for integer number of years as compared to how many he has survived. So if he has survived for 3.6 years, then the payments are 3. If he has survived for 2.5 years, then the payments are 2. So if he dies at time 2.5, then the present value of this thing can be expressed as A2, right? If you remember this notation from subject CD1, this is the present value of an annuity payable in arrears for 2 years, right? So this is the present value. Um, if he dies at time 3.6, the present value is A3, right? Similarly, so if I want to express this present value in terms of kx, it is nothing but A kx. If I try to check this, if I put 3.6 as the lifetime, if tx is equals to 3.6, then kx is 3, and your present value random variable is A3, right? So this is correct. So this is your present value random variable for an annuity uh, payable in arrears, right? Whole life annuity payable in arrears, and these payments they will keep on going as long as the person survives. So there is no time limit on such a contract. So the present value random variable is just AKX. If I talk about the EPV with you, the expected present value, it is the expectation of AKX, right? So if I want to write this in summation notation, it is k going from uh, 0 to infinity, ak into probability that k is equal to kx. That is your summation notation for this.
Okay, so if I want to simplify this, I know that this thing, probability that kx is equal to k, can be written as the probability of dying in the kth year. So this is nothing but k deferred qx, right? This is the probability that the person dies between time k and k plus 1, right? So probability of dying in the kth year, then only you'll get a curate lifetime of k. This multiplied with ak obviously again, and where k goes from 0 to infinity. At k is equal to 0, the value of this expected present value is just 0, because there are no payments. As we know, a0 is equal to 0. So when k is equal to 0, if the person dies, let's say at time 0.5, then k would be 0. So there would have been no payment. So the present value, the expected present value would be 0 itself, right? So now this is my expected present value, and I want to simplify this a bit further, right? So I will show you how to simplify this. For that, let's write the value of AK. We know that AK is equal to the discounted the sum of the discounted present value of all the payments that are happening. So it is basically V plus V squared plus v cube, right? So I am discounting the first payment with like one discounting factor, and then I'm discounting the second payment that is happening at the end of the second year with a discounting factor of v squared, and the third payment with a discounting factor of v cube, and this goes on till v to the power of k, right? So this is the definition of ak. If I substitute this definition here, then I get k goes from 0 to infinity v to the power of 1 plus v square plus v cube going up till vk, and this multiplied by k deferred qx, right? Now if I want to expand this fully, if I want to expand this term fully, this is nothing but uh, at 0 it is 0 deferred qx into nothing, obviously, right? V to the power of 0, so this is nothing. Add 1, it is 1 deferred qx into v, because it only goes up till v to the power of k, and k is 1 here. At k is equal to 2, it is 2 deferred qx into v plus v squared, because k is 2, and so on and so forth, right? So I'll write a few more for you. Plus 3 deferred qx into v plus v squared plus v cube, and this keeps on going till infinity, right? So that is the value, because this summation is going till infinity. Now if I try to see this, this is just 0, so I just cancel this out. With the term v, I'm going to change the order of summation here. See how I do it. With a v, I have if I take a v common out of all these terms, with a v I have 1 deferred qx plus 2 deferred qx plus 3 deferred qx going up till infinity, right? If I check with the v squared, there is no v squared here. There is a v squared here. So it starts from 2 deferred qx, and then there is a v squared here too. So there is one with 3 deferred qx2, and there would be one with 4 deferred qx2, obviously, and it keeps on going. With the v cube, similarly, it starts at 3 deferred qx, then there would be a 4 deferred qx, and this keeps on going, right? So these are the terms that I have. Now in order to simplify this a bit further, if I try to add all of these and write them as one term, we have seen this before too. This is just the probability that a person survives for 1 year and dies in the next year. This is the probability that a person survives for 2 years, and then this says the person survives for 2 years and he dies in the next year. This says that the person survives for 3 years and he dies in the next year. So this, all these possibilities added together, the person has to just survive for 1 year. So this is 1px, right? And if I check this one out, he has to survive for 2 years and then die, 3 years and then die, or these are all the other possibilities that can happen. Okay, as there are plus signs among these are all mutually exclusive possibilities being added, right? So the person has to survive for at least 2 years and then die in the next year, or he has to survive for 3 years, or he has to survive for 4 years. So, meaning that if we add all these probabilities, it is just 2px. That is, the person has to survive for at least 2 years. Similarly, this would be 3px and so on. Okay. So if I try to write this again, this is just v into 1px plus v squared into 2px plus v cubed into 3px, and this keeps on going, right? So if I rewrite this as a summation notation, this is j going from 1 to infinity, v to the power of jpx, and that is the definition for your uh, present value of a annuity, expected present value of an annuity of £1 payable in arrears till a life till a life aged X years is alive. If I try to interpret this intuitively, see, all this is saying is that if the life aged X survives for 1 year, there would be a payment of uh, one pound, and then it would be discounted back to time zero. So there is a V here. If he survives for time two, this is another possibility. Then this payment would be there would be one more payment, and this would be discounted back to time zero again. If he survives for 3 years, then there would be one more payment at the end of the third year, and it would be discounted back to time zero. So that is how it works. Okay, so this is very intuitive and very logical, this definition, and this is something you will have to understand and remember. Okay, so if I talk and just one more thing, the actuarial notation for this is just written as ax, right? So that is the actuarial notation, and the value of these are given in the tables. They are given in the tables of AM92 and ELT15. All the tables, they provide you with the value of these functions, so you can just use them directly. Okay. Uh, Apart from that, you will be specified in the question which table you are supposed to use. Okay, so that is the deal about them. Okay. Next thing is we discussed variance of the present value of these things. The variance of 8 AKX, that is what we need to find out now. So in order to evaluate this, I will have to convert this into somehow into assurances, because we know the value of the variances of all the assurance contracts. So in order to find the variance of annuities, we will use the fact that we can convert them into assurance contracts, right? So how will we do that? Let's see. We know that the definition of AN from subject CD1 is 1 minus VN upon I, right? We know that. So I'm just going to use this definition and expand this. So this is variance of 1 minus v to the power of kx upon I, right? Now this I will come out because it is in multiplication with this thing. So this will come out as 1 upon I square, and the inside thing would be variance of 1 minus v to the power of v to the power of kx, right? The next thing that happens is we know that variance is independent of origin, right? So 1 minus Vx, any constants added to the variance of any random variable, just it just goes, okay? It has no value there. For example, the variance of x square plus 2 is just variance of x square, right? So here also a similar thing would happen. It is I square variance of v to the power of kx, because this sign and this one here, it does not have any significance for variance. The variation remains the same independent of constants. So this is what I have here now. Something I know is that the variance of v to the power of kx plus 1 is equal to this is the present value random variable for an assurance contract. So this is equal to 2ax minus ax squared, right? This is something I know. So I'll manipulate this and get this somehow. So in order to get a plus 1 here, I'll divide and multiply this thing by v inside. So this would just be 1 upon I square variance of v to the power of kx plus 1 divided by a v. Okay. Now this v would come out again outside. So this would be 1 upon I square v square into variance of v to the power of kx plus 1. Right. This I square v square, if I multiply I square and v square, it's just I square and 1 plus I whole square, right? So this is I upon 1 plus I whole square, which is nothing but d square, right? So I can just write this as the variance of the discounting factor. It is 1 upon d square into this is the variance of an assurance contract. So I can just write this as 2ax minus ax whole square, right? And this is your variance of a present value of an annuity payable in arrears of £1. Okay, so that is the formula that you need to understand. So the next type of contract that we'll be discussing is a temporary annuity payable in arrears. This is similar to a whole life annuity payable in arrears, except for the part that it is limited by a term. There'll be a time restriction on this thing now. Let's see how. Let's say a person aged X buys a temporary annuity payable in arrears at time 0. That is that has a term of n years. So he'll be getting payments as long as he survives at the end of the years, but for a period of maximum of n years. There'll be no payment after this. Okay, in all the other aspects, this is similar to a whole life annuity payable in arrears, except for the part that there'll be no payments after time n. So if he dies here, let's say he dies here after 3 years, that is he dies at 3.6. Okay, at time is equal to 3.6, so he would have gotten three payments at time 1, at time 2, and at time 3. But if he dies at, let's say, time n plus 2 even, there'll be no payments after time n, so he would have gotten only n payments, right? So no payments are happening after time n. Okay, so in order to calculate the present value random variable, that is the first thing we need to do. We need to break time into two parts, um, based on the random variable kx, obviously. So when kx is less than n, the present value of this annuity would be similar to a whole life annuity. It would be akx. Okay, and when kx exceeds n or is equal to n, it would be nothing but an, because there would have been only n payments and no payments after time n. So that is the present value random variable. Now the tricky part here is the expected present value. The notation for the expected present value of an annuity, temporary annuity limited by a term of n years payable to a life aged x years, for a unit payment is AXN. Okay, so this is basically saying that there is an annuity and it is payable to a life aged x years as long as the life status x is active, and as long as the life status n is also active. Okay, as long as these both are active, this is payable. If x this status fails, then the payment cease because if the person dies, the payment cease. Okay, and if the time status n fails, that is if n years are over, the payment cease, right? So this is the notation that we'll be using for denoting the EPV of a temporary annuity limited by a term of n years, right? And for the present value random variable, there is one more notation that is usually used, that is a minimum of kx comma n. Now how did we get this? See, when kx is less than n, it is akx, right? And when n is less than kx, it is an. So it is basically a with a minimum of kx or n. So right, so whichever is less, that comes here. Okay, if kx is less, it becomes akx. You've seen this here, and if n is less, it becomes an, and you have seen this here, right? So that is how it works. Now, getting to the mathematics of EPV in the summation notation, we're gonna derive a formula for it. So the formula for this is obviously, let's see how it works. See, in order to derive the EPV, we will be using the present value random variable like we have always have, and we'll be dividing the summation into two parts. So going from obviously 0 to n, n minus 1, k is equal to 0 to n minus 1, because that is the last integer less than n. So when kx is less than n, the largest value is n minus 1. It is ak into the probability that the person dies in the kth year, so that is k deferred qx, and plus when kx is greater than n, so that is basically k going from n to infinity, greater than or equal to going till infinity, and it is a n into k deferred qx, right? So these are the two parts of this thing, and now I'll expand this like I did in the previous question, and I'll just get you a simplified form of this thing. Okay, and the mathematics here is a bit tricky. You might want to go through this two or three times in order to understand this. So pause your video, go back and check, do this 2 to 3 times so that you know you're sure you perfectly get it. Okay. So let's see what's happening there. See, this an is a constant with respect to k, so this will come out, and I'm gonna leave this the same for now. So this is k going from 0 to n minus 1, k deferred qx into a k. So this thing, it just an comes out. Okay, so plus an is coming out, and I've got a k going from n to infinity and k deferred qx. Now we know that this term is just the sum of uh, n deferred qx plus n plus 1 deferred qx plus n plus 2 deferred qx going up till infinity. So this says that a person survives for n years and then dies in 1 year, or he lives up till n plus 1 year and then he dies in the next year, or he lives up till n plus 2 and then he dies in the next year. So this is basically the probability that the person has to survive for at least n years. So this is nothing but npx. We've done this before into an, right? This term simplifies to this. Now about this part of the equation, we know that ak is just a sum of the discounting factor, that is v's. So I'm going to write this in terms of j here, in terms of the discounting factors. Okay, so I'm going to do that. So it is k going from 0 to n minus 1, k deferred qx, and I introduced a new variable here, that is j, and where j goes from, basically j is going from 0 to, let's say, it is going till k minus 1 v to the power of k. Okay, that is where v to the power of j plus 1, I'm sorry, v to the power j plus 1. I'll show you how did I get this. See, basically ak is equals to v to the power of 1 plus v to the power of 2 plus v to the power of 3 and so on, right? That is the definition of going up till v to the power of k, right? That is the definition of ak. So I wrote it in terms of j, such that I've written it as v to the power of j plus 1, where j goes from 0 to k minus 1. So when I put 0 in place of this, I get v to the power of 0 plus 1, that is v1. And then when I put 1 in place of this, I get a v to the power of 1 plus 1, that is 2, and so on and so forth, going up till v to the power of v to the power of k minus 1 plus 1, that is v to the power of k, right? So I've just changed this form. and I'm gonna rewrite this so that it is clear. K goes going from 0 to n minus 1, k deferred qx into sum of j going from 0 to k minus 1 v to the power of j plus 1 plus an into npx, right? So this is what we have. So now we have two options, right? We have two options. We can either expand this thing, this v, and then take all the kx's common, like I did in the previous type of contract that was a whole life annuity contract. Or I can do one interesting thing here. This thing, if you are a member of the Institute of Actuaries of India, you must have studied the fact pack and the stats pack in ASET, right? Fact and stats pack in ASET. So if you have studied that, you must know the method for changing the order of summation. So I'm going to change the order of summation here. I'm going to interchange J and K here, and I'm going to teach you how to do it. And this is a easier way, than rather than expanding the entire thing and then taking everything common. There's a easier way to you know interchange the order of summation, and we can proceed with that, right? So I'm going to tell you that how to change the order of summation. Okay, so let's just see how do we do that. Okay, so this is just saying that k is going from 0 to n minus 1. Okay, so you can also solve this using the way I did it in the previous question. You can just expand these j's and you can expand the k's, and then you can take common out all the j's, and you will get something, and you can proceed like the last question, but this is an easier method you can use. Okay, so k is basically going from 0 to n minus 1, and j is going from 0 to k minus 1. So wherever the last value of k is, j is just 1 less than that. Okay, so j goes from 0 to k minus 1, right? So now what I want to do is I want to take a longer interval for j and a shorter interval for k. That is what I want to do, and I want to see here what is happening is j is dependent upon k, right? So I want to make k dependent on j, and I want to take j outside. Okay, so if I want to do that, I'm switching the order of summation. Outside there'll be obviously j. So j is going from now it is c. It is dependent upon now j is independent, and k is dependent upon j. So basically j will have to go over its range, uh, which is independent of k. So j cannot be equal to something that is k. Okay, that is function of k. So j cannot be equal to k minus 1 now. So now j will go from 0 to the highest value that j can take. So the highest value that j can take was n minus 1 here, because the highest value for k, you see, it was n minus 1. Okay, and when k is equal to n minus 1, j was equal to n minus 2, right? Because j is 1 less than k, so j will go from 0 to n minus 2, right? So that is what will happen, and that is the range for j, right? So we have got a v to the power of j plus 1 that is going over this range. Okay, now I'll express k in terms of j. Okay, so k is no more independent. So I have covered the range of j going from 0 to n minus 2. Now I'll have to take the range of k which is dependent upon j. Okay, so where will k start from? K will start from n minus 2. Uh, I'm sorry, k will start from j plus 1, right? Because k can take the minimum value that is 1 more than j. So k will be dependent upon j, and k will take a value j plus 1, and it will go up till its highest value, which is the same as before, that is n minus 1, right? That is how now k is dependent upon j. So and the reason I didn't take it going from 0 is because that range is already covered by j. I'll take it to be 1 more than j, and then I have to take it up till n minus 1, because this area going from n minus 2 to n minus 1, this area is not covered by j. Okay, so that is what is done here. Okay, so k is dependent upon j, and k is going from j plus 1 to n minus 1, and then the same as it was k deferred qx, right? So this is what I have. Put it in a box so that it is clearer. Okay. So this is the term, and there was one more term, that is an into npx. Okay, so this is what is happening here, and I think you will understand it. But if you can't, just go through it again. See, what we do is, when we change the order of summation, I'll be doing this again in further questions too. Uh, or when we change the order of summation, here j was dependent upon k, and what I want to do is I want to make j independent, and I want to make k dependent upon j. So I give j the ultimate range, that is j goes from 0 to whatever the highest value it can take, that is n minus 2, and it is independent. And then I just take k based on j, and then I take it up to its highest value. Okay, so this thing, that is how it happens. Okay, so that is what happened here, and now I can basically just expand this part. Right, j is going from n minus 2 to v to the power of j plus 1, and I'm gonna okay, this is j plus 1 deferred qx plus j plus 2 deferred qx going up till n minus 1 deferred qx plus an into npx. Okay, so now what happens here is basically that qx is going deferred qx's are going from j plus 1 up till n minus 1. So what this is saying is that a person has to live for at least j plus 1 year, and then die in that year, j plus 2th year. And then this is saying that the person has to live for at least j plus 2 year, and then he dies in the next year, and going up till n minus 1, that he has to live for n minus 1 years, and then he can die in the nth year. So what this is saying is that the person who is aged x, he has to live for at least j plus 1 years, but not more than not more than n years, right? This is covering these terms, all of these terms, mutually exclusive terms, they are covering the area from j plus 1 going up till n. See, you can see this. See, this is saying that he has to live for j plus 1 year, and then die within the next year, j plus 2 years, and then die within the next year. And this is going up till n minus 1 year, and then he can die up till time n. So this is the area that is covered. So if I try to express this in terms of the p probabilities, this just becomes j is going from n minus 2 to v to the power of j plus 1 into the probability that he survives for j plus 1 years minus the probability that he survives for n years. So this is just j plus 1 px minus npx. Okay, so that is what this is. And then this term remains the same. So this is just an into npx. The next thing I do is that I just open these terms up. I just multiply this thing inside. So j is going from 0 to n minus 2 v to the power of j plus 1 into j plus 1 px minus j is going from 0 to n minus 2 j v to the power of j plus 1 into npx. Okay, plus with this an, I just open it up and write it in terms of v's, that is discounting factor. So I can write this as j is going from 0. Since I have to adjust this with all these ranges, uh, I'll be taking this in form of j only, and so that I can adjust it, and it will go from 0 to n minus 1 v to the power of j plus 1. See, that is what this becomes like before, and this is npx, right? So now I'll have to do some sort of adjustment here. Let's see what I can do here. Mm, these two terms, this term and this term, they're almost the same. The only difference is that there are n minus 2 terms here and there are n minus 1 term here. Okay, so all these terms cancel and only what remains is when j is equal to n minus 1 term. This only one term remains, that is j is equal to n minus 1. So if I cancel these out and I will give you the result would be j is going from 0 to n minus 2 b to the power of j plus 1 uh, j j plus 1 px. Was it j plus 1? Yeah, this was j plus 1 px into, not into, plus when I put n minus 1 in place of j, this is just v to the power of n into npx. Okay, so this is what I have. Now there will be a further adjustment and this would be the last of it. Okay, so I'm going to write this in terms in a different term. I'm going to change the range from j is equal to 1 to n minus 1, and from v, so this v to the power j plus 1, I've just added 1 in these two in the range, so I can remove 1 from here. So this is just v to the power j into jpx now. Okay, and this v to the power of n npx, same as before. Now I want to add these two terms. This is j going from 1 to n minus 1 b to the power of j jpx, and this is the same as these terms when j is equal to n. Okay, so I've got one more term here, and then j will go from 1 to n b to the power of j into jpx, and this is your final answer. And as you would have expected, this is very similar to a, if we compare this to a whole life annuity. A whole life annuity is j going from 1 to infinity v to the power of j into jpx, and this is just going from 1 to n. So these are very similar, and this is like logical because it is limited by a term of n years. Okay, and the notation for this is obviously axn, and for this one was ax. Okay, so before discussing the variance of the previous contract, that was a temporary annuity payable in arrears, I'm going to discuss with you annuities payable in advance, and then I am going to discuss the variance of the temporary annuities together as a single topic. Okay, because their derivation is quite connected. For now, I'm moving to a new topic, that is that is the third type of a contract, that is a whole life annuity payable in advance, right? So this type of a contract again, you must remember annuities payable in advance from subject CT1, they were A due N. So what is happening here is there are similar payments payable when a life is alive, but these payments are payable in advance. That is at the beginning of the period. So for example, a life aged X takes a policy at time 0, and he will be getting on payments uh, at the beginning of the terms. Okay, so even if he dies at time 0.5, that is after 6 months of the policy inception, he would have still gotten one payment here. There would have been one payment here at time 0, and so on and so forth, right? So the payments start at time 0 itself. So even if I die at time 2.5, right? If this person dies at 2.5 time, I would have gotten three payments. There would have been a payment at time 0, there would have been another one at time 1, and there would have been another one at time 2, right? So three payments to a guy who lives for 2.5 years, right? So basically, if I want to write the present value random variable, um, let's try to understand this. How will I get this? For a person who has died 2.5 years, it is basically coming out to be a due 3. because there have been three payments, right? And for a person who is has died at 0.5 years, it is coming out to be a due 1, right? Because one payment. This is not the period. This is the number of payments. You need to understand. These are the number of payments, okay? So that is how it works. So for a person who has a curate lifetime of kx age, he will have a number of payments equal to kx plus 1, because there is one extra payment at time 0 to now. Yeah. So this would be a due kx plus 1, the present value random variable. Okay. So that is how it works. One more payment than your curate lifetime. If your curate lifetime is 2.5, if your lifetime is 2.5 years, the curate lifetime is 2 years, and you get three payments: one at time 0, one at time 1, and one at time 2. Right? Three payments. So that is how it works. Okay, now talking about the EPV, the notation, the actual notation for the EPV is AX, and it is the expected present value of it is the expected present value of this type of a contract, and I can write it as expectation of A due KX plus 1, right? That is what I can write this as. So now expanding this in the summation form without further delay, this would be k going from 0 to infinity, obviously a due, obviously k plus 1, and like always k deferred qx, right? So this is what I have. Okay, now I'm going to show you the magic of changing the summation sign again. Before that, I want to expand this a due kx plus 1. So basically what a due k plus 1 would be, it would be 1, because this would be the payment at time 0, the present value of the payment at time 0, plus v square going up till v to the power of k, and not k plus 1, because there are a total of k plus 1 payments, and these are k payments, and there is one more payment here, so they make up k plus 1 payment. So don't get confused. They will go up till only time, the last payment would only be discounted with the time of k. Okay, so that is how it works. So this is the expansion, and if I want to write this in summation, I can just write it as j going from 0 to, let's say j is going from 0 to k, and v to the power of j, right? That is how I can write this, because at time 0, it would this term would just be equal to 1, and at time k this would be equal to v to the power k. Okay, so then I can just expand this k going from 0 to infinity, and the sum of j going from 0 to k v to the power of j into k deferred qx. Okay, so this is what I have. Now I'll be changing the order of summation like I did in the previous type of contract. See, what is happening here is that k is going from 0 to infinity, right? You know that k is going from 0 to infinity, and j is going from 0 to k. Okay, so now I want the value of k to depend on j, and I want j to cover the entire range. So first I determine the range of j. Okay, so the range of j would be going from 0. Obviously it would start from 0, and it will go up till the highest value it can take. So it is just basically equal to k, right? J is equal to k. So the highest value that k can take is infinity. So the highest value that j can take is also infinity. Okay. Now for k will start where j ended. So it would be j, because k and j are same at j's highest value, and it would also go on till infinity. So that is how I change the order of summation. This is just k deferred qx, and I've got a vj here. Okay. Now we know I'm not going to explain this again because I've done this like 10 times now. So this term k deferred qx going from j to infinity, it is nothing but the probability that a person lives for at least j years. So this is just jpx into vj. If you didn't get this, just go back and just try to understand this. I've explained this a lot of times. I'm sure you did. Okay, so this is my definition for the present value or expected present value of this kind of a contract. And if I compare this as against the present value, the expected present value of, let's call this a due x, okay, because that is the notation for it. If I compare it against AX, that was the present value of a whole life annuity payable in arrears, that was just J going from 1 to infinity. Okay, there was a 1 here, JPX into VJ. So the only difference between these two guys here is just that is just the term where J is equal to 0. Like that is the difference. And when J is equal to 0, the value of these terms would be JPX would be the probability that the person lives. It would be 0px into v to the power of 0. So this is just the probability that a person aged x lives for at least 0 years. So obviously at least 0 years it would be 1. And v to the power of 0 is also equal to 1. So this is just 1. So conclusively what I can imply from this is that a due x is equals to ax plus 1. Okay, and this is very logical and very obvious. I'll tell you why. See, what was happening under a whole life assurance payable in arrears were infinite payments, right, till till this person survives. uh, and these payments were at times 0, 1, 2, 3, so on and so forth, right? And what is happening under this new type of contract, that is payable in advance? It is this is arrears and this is advance. What is happening here is there are similar infinite payments on survival. Okay, but these start at time 0 itself. Okay, so if there is this person, okay, if a person has survived for 3 years, he got payments, and he is getting let's say payments of £1. If he is getting payments of £1, the three payments that the payments he would have gotten if he died at, let's say, um, 3.6 years. Okay, let's call it that he has died at 3.6 years. So he would have gotten one payment at 1, whose present value would be V. He would have gotten one more payment at time 2, whose present value would be V square. And he would have gotten one more payment at time 3. Okay, and for this guy here, he would have gotten 4 payments. He would have gotten one payment at time 0, one at time 1, one at time 2, and one at time 3. So their difference, if I take a difference, if I subtract these two, it is obviously 1, because these terms they cancel out. Okay, so it is very logical. Think about it. These contracts are just the same, except for the fact that um, the payments here are starting in advance at time 0 itself, and rest of the payments depend on the survival of the life similarly. Okay, the next thing I want to talk to you guys about is the variance of this contract. So it is the variance of a kx plus 1, right? That is what it is. And a due kx plus 1, I'm sorry, because these are payable in advance. So if you remember the formula for a due n from subject CD1, it was just 1 minus vn over d. Okay, that was the formula that we had there. If I try to write this in this form, it would be 1 minus v to the power of kx plus 1 over d. Okay, so that is what we have, and we want to take the variance of this thing. So variance of this. So taking the variance of this term, variance of 1 minus v to the power of k x plus 1 over d. Um, if I take d out, it would be 1 upon d square, and variance of 1 minus v to the power of kx plus 1. And this would again obviously be the variance of this thing. This constant just goes, so it is the variance of v to the power of k x plus 1. And I can recognize this part. This is just 2ax minus ax, that is ax square, that is from the uh, variance of v to the power of k x plus 1 was the variance of a whole life assurance contract, right? So this is just 1 minus 1 upon d square into 2ax minus ax whole square. And if you just turn back your pages and you check, this is the same as the variance of a whole life annuity payable in arrears. the variance of whole life annuity payable in advance and the variance of a whole life annuity payable in arrears are the same. And the reason is very obvious because amongst these two payments, all the payments are same, just that there is one more payment at time 0, which is a constant obviously, because the payment at time 0 payment is not dependent on survival, not dependent. Okay, as soon as you take the contract, you get a payment under an annuity payable in advance. Okay, so it is not dependent on your survival, and that is why it is a constant, and that is why the variance of these two contracts are just the same. Okay, so it is very very logical.
Okay, guys. So the next kind of contract that we talk about is a temporary annuity payable in advance. So as the name suggests, this is similar to a whole life annuity payable in advance, except for the fact that it is limited by a term. That is, it is limited by a time period. So in order to understand the contract, let's draw a number line. Okay, so let's say a life aged X at time 0 buys a temporary annuity payable in advance for n years. Okay, so this guy will get payments as long as he is alive at the beginning of the years, but for a maximum period of n years. So there'll be no payment here. There'll be no payments after n years. Okay. For example, if he dies at time 3.6, he would have gotten four payments by this time: one, two, three, and four. One at time 0, one at time 1, 2, and 3. Right. So he would have gotten four payments. If he dies at let's say time 4.5, he would have gotten five payments by now, because he would have gotten this payment too. If he dies anytime after n, he would have gotten n payments only. Okay, so that is how it works. Okay, so maximum number of payments are n, and the last payment would happen in the nth year. Okay, so that would happen at time n minus 1. Okay, it would not be at time n, it would be at time n minus 1, because the maximum number of payments are n, and they are happening for nth year. But as since they are at the beginning of the periods, the last payment will happen at time n minus 1. Okay, keeping all this in mind, let's construct the present value random variable. So the PVRV is obviously for time 3.6 it was a due 4. For time 4.5 it was obviously a due 5. Okay, so this is just one more than the curate lifetime. We can write this as a due kx plus 1, similar to a whole life annuity payable in advance when kx is less than n, and when kx is greater than equal to n, this is just a due n. Okay, so there were n payments. Okay, let me try and explain this to you once more. So in order to understand this, let's take three examples. Let's say n is equal to 20. Okay, so if this person dies at time 20, um with okay, let's write one more notation for this, and then I'll explain it to you. So this can be written in one more way. This can be written as a due uh, minimum of kx plus 1 comma n. Okay, so that is how I can write this. So the reason I can write this way is, let's see how this works. Okay, let's say n is equal to 20. Okay, so if n is equal to 20, if the person dies at time 20, um kx plus 1 would be equal to 21, but n would be equal to 20, so he would get minimum of both, that is he would get 20 payments, which is obvious, which is correct. Okay, so if n is less, it is this one, a due n. If he dies at time, let's say if he dies at time 19.2, then curate lifetime would be 19 years, and kx plus 1 would be 20, and n is also 20, so we can choose either one of them. Okay, and when t is equal to, let's say, 21 years,
then kx would be obviously equal to 21 years again, and that would be 21 plus 1, that is 20 a due 22. So we will and so this would be 22 and this would still be 20. So we will choose a due n because n is lesser than kx plus 1. So we can write it like this too. So it is a due minimum of kx plus 1 comma n. Okay, so that is a way of writing the present value random variable. Now moving on, let's talk about the expected present value. Okay, so the expected present value would obviously be divided in two parts, going from k is equal to 0 to n minus 1, that is when less than n. Okay, so n minus 1, that is the last integer before n. So it is a k plus 1 k deferred qx. Okay, and when k goes from n to infinity, it is a due n into k deferred qx for obvious reasons. Okay, so this is what I have here. Okay, now let's try to simplify this a bit further. Okay, here we can write this k a due kx k plus 1 as something. Okay, what can we write it as? Okay, going from 0 to n minus 1, I can write this as, since there are k plus 1 payments, okay, and the first one is happening at time 0, so we can write this as a sequence of v to the power of 0 plus v to the power of 1 going up till v to the power of k, not k plus 1, k, because the total number of payments are k plus 1. Okay, but the last payment will happen at time k. See, this is one payment and these are k payments, so I have got a total of k plus 1 payments, but the last payment will happen at time k. So I will take a j which will go from 0 to k and v to the power of j obviously. Okay, and this is still k deferred qx, and this part I will keep the same except for the part I'll take a no I won't do anything to this part, so I'll keep it just the same, a n, and this is k deferred qx. Okay, so this is what I have here, and let's try to simplify this a bit further. So the next thing I do is obviously I change the summation notation. So going from I've got k which is going from 0 to n minus 1. Okay, so this is the extension of k, and then I have got j which is going from, okay, which is going from 0 to k. Okay, because it is going from 0 to k, it can take the highest value equal to k, that is n minus 1. Okay, so this is what I have. Now I want to change this. Okay, so I if I want to change this, I want to write it in terms of j independently. So if j is independent, it will go from 0 to its highest value, that is n minus 1, and now k is dependent on j, so at the minimum point k is equal to j and it will still go to its highest value, that is n minus 1. And we have got v to the power j here, and we have got k deferred qx here. I'll have to interchange these. I'll write k deferred qx first and then I'll write v to the power. Okay. And with this part, I can just write k is equal to n to infinity, and I can write a due n as going from j is equal to 0 to obviously it will go till n minus 1, because there would be total of n payments starting at 0. So 0 1 2 3, and it would go up till n minus 1, so that the payments total up to n, so v to the power of j. Okay, this is what I have. Similar to this, a similar explanation operates here, and k deferred qx. So this is what I have now. Now let's just see, let's just try to simplify this. See, I've got j going from 0 to n minus 1 vj here, and I've got j going from 0 to n minus 1 vj here. So I'll take this common. Okay, taking this common, j is going from 0 to n minus 1 vj is taken common. So what I'm left with inside is k going from j to n minus 1. Okay, k is going from j to n minus 1, and I've got k deferred qx, and I will add this to
I'll add this to the remaining part here, that is k going from n to infinity, and k deferred qx. Okay, so these are the terms that I have now. So these two terms, they add up, they naturally add up. K deferred qx is same, and just that k is going from j to n minus 1 here and n to infinity here. So I can just write this as j is going from 0 to n minus 1 v to the power of j, and I can write this as k is going from j up till infinity. Okay, all these values are taken up because see, you see here, j was going from k was going from j to n minus 1, and then I added another range where k was going from n to infinity for exactly the same thing, so they both add up. Okay, so they, it goes from j all the way up to infinity, and this is k deferred qx. Okay, so this is what I have here, and since I have this, I know what this means. This means that the person has to live for at least j years, and then he can die anytime after this. So this is j going from 0 to n minus 1, v to the power of j into j px. Okay, so this is what I have, and this is your definition for a due xn. Okay, so this is your actual notation, okay, for the EPV of a temporary annuity payable in advance of £1. Okay, so this is your actual notation. Okay guys, so the next thing I want to do is a comparison between a temporary annuity payable in arrears and a temporary annuity payable in advance. So if I talk about the expected present value of a temporary annuity payable in advance, it is, as I just proved, it is j going from 0 to n minus 1 v to the power of j and jpx, because the payments start at time 0 itself and the last payment is at time n minus 1, right? And with a temporary annuity that is payable in arrears and there are n payments, so this is denoted as AXN. Okay, and the EPV formula is where j goes from 1 to n v to the power of j jpx. So all we see is that there is only a difference of range between these tools. This starts at 1, goes up till n, and this starts at 0 and goes up till n minus 1, right? So if I take the difference, see, I know that ax plus 1 was just equal to a due x. So is it also true for these two? Are they only differing by 1? Obviously they are not. Obviously they are not. So let's check what is their difference. So if I take a difference, a due xn minus a xn. Okay, if I take this difference, this is basically equal to, see, what they differ is there is a payment at time 0 in this one. So if I put 0 in place of this expression, so it just becomes 1, and at time n this is paying something, but this is not paying anything. So they're differing at time n too. Okay, so except for time 0 and time n, they are just the same. Okay, uh, between time 1 and n minus 1, they are just the same. They differ at only 0 and 1. So at time n, it is basically v to the power of n into npx, putting an n in place of this formula. Okay, so this is the difference of these two formulas, and okay, they don't differ by 1. These two guys did differ by 1 because they are both infinite payments, so there was no question of a payment differing at time n or time infinity. Okay, because if they go infinite, if this has infinite payments and this has infinite payments, there is no question of the last payment. Okay, so they just differed by 1, but now there is the last payment, so they differ by the last payment too. Okay, so this is 1 minus v to the power of n npx. Okay, and this is your answer for question number 2.4 of the core reading. They've asked you to compare these two values, and this is your answer for question number 2.4 of the core reading. Okay, and if I talk about question number 2.5 from the core reading, it asks me that can you give an expression for ax
n plus 1. They want us to give a single expression for ax n plus 1. So if I want to give this, this is basically where k goes from 1 to n v to the power of j into jpx, right? And this is just 1. So if I want to add this to this, I can just write this thing, this 1, as I can write this 1 as v to the power of 0 px, right? Because this is just 1. The probability of a person aged x living for at least 0 years is 1, and v to the power of 0 is also 1. So I can write it as this. So I will write it as this. This is k going from 1 to n v to the power of jpx plus v to the power of 0 px. Okay, and if I do this, see, these two are same things. This is just at 0 and this is starting from 1. So I will just add the 0 term to it. So k going from 0 to n. Okay, oh, this was j, I'm sorry. So this was j here, and this was j here, and this was also j here. Okay, so j going from 0 to n, and this just becomes v to the power of j um, into jpx. Okay, and this is what I have, and they want me to give a single expression for this term. So if I want to give a single expression for this term, I will have to compare this against this. Okay, I know that a du xn is equal to the sum of j going from 0 to n minus 1 v to the power of j jpx. Okay, and this is going from 0 to n, except that everything is same. So it's just the final limit. Okay, the limit of this thing is just one more than that. Okay, so this thing, it turns into a du x, and I had an n here before. I have an n plus 1 because this was going from 0 to n minus 1. This is going from 0 to n, so I've got n plus 1 here. Okay, and this is your answer for question number let's say 2.5. Okay, so this is your answer for question number 2.5. Okay, next thing I want to talk about the is a topic I had left before. This is the variance of temporary annuities. Temporary annuities. Okay, so I want to talk to you about the variance of temporary annuities. And okay, first I'm going to discuss the formula for variance of temporary annuity payable in advance. So that is the first thing, and I am going to use this in advance formula in order to derive the variance for a temporary annuity payable in arrears. That is why I had left the temporary variance of a temporary annuity is payable in arrears before, so that I can just derive it using this method. So if I take the variance of this, so the present value random variable was obviously a due minimum of kx plus 1 comma n, right? Just check it out, go above and check it out. I hope you remember it. Okay, so this is what I have. Now expanding this is just the variance of 1 minus v to the power of minimum of k plus 1 comma n, and I have got a d here. Okay, so if I take the d out, this is 1 over d square, and I can just write this as variance of v to the power of minimum of kx plus 1, because variance is independent of origin. Okay, so that is something that happens here. And this expression, this v to the power of minimum of kx comma n, this is something you must recognize. This is the EPV of an endowment this is the, yeah, this is the present value random variable of an endowment assurance. And I'll prove this to you. I'll show you how it is. See, this is saying minimum of k, v to the power of minimum of kx plus 1 comma n. So this can be expanded as v to the power of kx plus 1 when kx is less than n, and v to the power of n when kx is greater than equal to n. Okay, so this is the same as an endowment assurance that pays amounts at the end of the year if you die before time n, and if you die at or after time n, you just get a maturity benefit at time n. Okay, so this is an endowment assurance, this is PVRV. So I'll just, so variance of this thing is just the variance of an endowment assurance. So that is 1 over d square into 2a x n minus a x n whole square. Okay, so this is what I have here, and this is my result. Now if I talk about the variance of temporary annuity payable in arrears, so in arrears, if I talk about this, variance would be variance of a minimum of kx comma n. This is the expression, right? And in order to expand this, I can just write, I just proved this, that a minimum of kx comma n is nothing but a due. This is also true in case of PVRVs, like it is in the case of EPVs. So this is a due minimum of kx plus 1 comma n plus 1, and there was a 1 added to this, right, earlier. So this would be this minus 1. Okay, so this is just this minus 1. Okay, I just proved this in the last part, question number 2.5. I proved it for EPVs, and this is also true for the present value random variable. So I can just write this expression as this expression. Okay, so this is just variance of ADU minimum of kx plus 1 comma n plus 1 minus 1, right? Because all this is saying is that that you'll get a k plus 1 or n plus 1 payments um, when till you are alive at the beginning of the years, and if I deduct 1 from this, I'll just the first payment would be removed and I will still be getting the same payments. Okay, so that is how it works. Okay, I have already proved this, not discussing it any further. So this is just variance of a due minimum of kx plus 1 comma n plus 1, because it is variance is independent of origin. Okay, now in order to simplify this, I've just got a variance of 1 minus v to the power of minimum of kx plus 1 comma n plus 1. Okay, this is what I have, and divided by d, obviously. So what I have is 1 over d square into the variance of v to the power of minimum of kx plus 1 comma n plus 1, right? And this is this is the variance of this is the variance of an endowment assurance with a term of n plus 1 years. So this is nothing but 1 over d square 2a x n plus 1 minus a x n plus 1. So that is what I can write, this a plus a x n plus 1 whole square, right? So this is what I can write this variance as, and that is how we do the derivation. Okay, so this was the variance of a temporary annuity payable in advance. This was for one in advance, and this is your variance for annuity payable in arrears. Okay, thank you. Okay, so the next thing we talk about here is a new kind of a product that is called as deferred annuities. But before discussing that, I would like to discuss some important thing with you. Uh, a student of mine asked me that do we need these derivations and proofs for the sake of the exam? Okay. So like there's no straight answer to that. See, the thing is that IFOA in particular, the Institute and Faculty of Actuaries, UK, they do not ask for proofs usually. They just have applications of these formulas in their exam. Okay, so mostly if you're giving the exam from IFOA, you wouldn't be getting a lot of proofs. But institutes like Institute of Actuaries of India, proofs often feature in their papers. Okay, and you need these proofs if you are going to appear from II. Okay, so you do need these proofs for II, but you don't need them for IFOA. You just need these final results, and you should be able to know how to apply them. Obviously, we'll be learning them when we will do the exam questions. Okay, and for more information about such sort of things, you can always refer to the past exam questions that are given in the revision notes, because you can get a better idea from there. Also, I insist on it that you guys should, try and understand these proofs, because that is the beauty of subject CD5, and that is the beauty of actuarial science, that you are understanding everything. You do not need to learn things. At least if you do not get these proofs, you should intuitively understand the final formula. Okay, but the way I am explaining these, I'm trying to make them as simple as possible with my timelines and my method. So I want you to be able to appreciate that. I do not want you to cram things, and I want you to understand these things. So I hope you would, respect that. Okay. So now moving on to the topic, deferred annuity. Annuity is payable in arrears. Okay. So like deferred assurances, deferred annuities are contracts which do not start at the beginning of the term itself. They are deferred or delayed by a period. Okay. So let's talk about this. Uh, let's say a man aged X buys an annuity, a whole life annuity that is deferred by a term of n years. So there is a deferment of n years. So if this annuity is payable in arrears, the payments would start happening at time n plus 1, n plus 2, because this is deferred by n years. So at the end of the first year, the payment would happen at time n plus 1, then there would be a payment at n plus 2, then there would be a payment at n plus 3, and so on and so forth. These payments will go up till infinity, right? So the first thing that we always discuss here is the present value random variable. Okay, in order to understand the present value random variable, see, um, this person, he is alive here, but there would be no payments on this part of the timeline. Okay, no payments. And after that, if he survives after n years of a period, then there would be payments at time n plus 1, n plus 2, and n plus 3, as long as he survives, right? Like all annuity contracts. So let's assume that a guy he dies at time n plus 2.5. So the guy is dying at time n plus 2.5. Okay, so now let's see what would be the payment made to him. See, he would have received two payments by this time, that is one at time n plus 1 and one at time n plus 2. So if I want to calculate the present value of this payment, the present value at time n would be a2, right? Because there have been two payments, and then I need to discount this back to time 0, because I am valuing these present values at time 0. So there would be a factor of Vn multiplied with it. Okay, so that is what the present value of this contract to this person would be. Now, if we talk about in general, if I try to express this in terms of kx, then the present value random variable is just v to the power of n a kx minus n. Okay, so that is your present value random variable um, when kx is greater than equal to n, and when kx was less than n, then it was 0. Okay, so that is your present value random variable. When we were here, when we were less than n, there was no payment, so that is 0. And if we are greater than n, then this is your present value. Okay, and I will prove that this is the present value that you need. The way I would prove that is, let's just see this. Okay, I took an example here, so I would prove it for the same person. Let's see. See, the value of kx for this person was what? the value of kx for this guy was he survived for n plus 2.5 years, right? So kx for this person was n plus 2, okay? And then the present value would be minus n into v to the power of n, right? So that is your value. And if I simplify this, this is just n and n cancel, and it's a2vn, right? So we get the same value from this formula and this generalized formula, right? So this is pretty much correct. Okay. So now let's just start talking about the expected present value that we get, and in this case it is a bit complicated, so I want you to pay more attention here. So expected present value obviously is going from 0 to n would be 0, we know that. Going from n to infinity, going from k is equal to n to infinity, the expected present value is v to the power of n a k minus n, right? So this is what we have here. Okay, so this is your expected present value. Now if I want to simplify this, if I want to simplify this a bit, let's say I'm going to expand this part. Okay, so I'm going to expand ak minus n. So if I want to expand this, see, ak minus n is a sequence of the addition of v1 plus v2 plus v3, all these payments going up till v to the power of k minus n, right? So that is what this is. So I am going to write this as k going from n to infinity, and okay, and I am sorry, I forgot to write k deferred qx here, that I missed. Okay, so I am multiplying it right now. Okay, this is the sequence that I need. Okay, this is the sequence that I need, and okay, so I'm going to put this here. The Vn comes out because it is a constant with respect to k, and this thing, ak minus 1, we can just write this as the sum of j going from 1 to 1 to k minus n v to the power of j, okay, into k deferred qx. So that is what I have here. That is what I have here. And now what I am going to learn is to obviously we know how to change the order of summation. So let's just do that. Here k is going from n to infinity. So I've got n and I've got infinity. K is going between these two. And I have got a j that is going from 1 to k minus 1, k minus n. I'm sorry. Okay, so j is going from all over the values from 1 to k minus n. Okay, so the maximum value that j can take is infinity minus n, that is infinity itself. Okay, so that is what is happening here. Now let's change the order of summation. So this is v to the power of n. um, Outside I'll have j, obviously j going from its lowest value, that is 1, to the highest possible independent value it can take, that is infinity minus n, k minus n. The highest value is infinity, so infinity minus n is infinity, right? And with k, what I have is k going from n to infinity earlier, so now it would depend upon j. So when, see, we know that j was k minus n, right? So k would be j plus n. So its dependent value on j would be j plus n, and it would also go up till infinity, right? So that is what we have here, and I had a k deferred qx, and I had a vj. Okay, so this is what we have here. Okay, now let's just try to simplify this. I've got a k deferred qx going from j plus n to infinity, right? So I've got a vn here, and I've got j is equal to 1 to infinity. So this part, it just becomes, we know what it becomes. It becomes j plus npx, right? Because this is the probability of a person living for at least j plus n years, and this multiplies with j, v to the power of j. Okay, so this is what I have. Now, if I want to simplify this, I need to remember something. Okay, the thing that you need to remember is the formula for AX. AX is just j going from 1 to infinity, uh, jpx into vj, right? So this formula looks a lot like this part, except for the fact that we have got a j plus n in place of j. So if we compare these two, the only difference we have, if I compare this with this, the only difference I have is that there is a j plus n instead of this. So I'm going to somehow try and convert this into a form of this. So what I do is, we know that x p j plus n can be written as, I have given you this formula already, px n into x plus n and a j here. So all this is saying is the probability that a person lives for j plus n years is equal to the probability that the person lives for n years into the probability that the person aged x plus n lives for j years, right? So that is what it is saying, and I can just replace this formula, and this would be a constant, so I'll take it outside. So this is just Vn into npx. I've taken the constant outside, and j is going from 1 to infinity, and see, I've got a j px plus n into vj. Now, if I compare this with this form, I have just got a x plus n in place of a x here, right? So I can just write this to be equal to ax plus n. Otherwise, it is same as this in all aspects. So I'll write this as ax plus n, okay? And that is my final result. Vn into npx into ax plus n, okay? And this is your formula for the present value of a deferred annuity. This is the actual notation for it and deferred AX, and this is the formula for the present value of a deferred annuity, and it is very logical. You see, it makes sense. It is saying that a whole life annuity starting from the age of x plus n is discounted back till time 0 for n years, so discounted for n years, and it is multiplied with the probability that the person aged x lives for at least 10 years. So if this guy is, he is at time 0 and he's aged x, and the payments are starting at this time his age is x plus n, so the present value at this time is ax plus n, right, of a whole life annuity. And we discount it back to v with vn factor, and then we multiply it with npx, because we need to multiply the probability that he'll survive from here to here till n, right? So this formula is very logical, right? So you again don't need the derivation, you don't need to remember the derivation. All you need is this final formula, and you are through, okay? So this final formula is all you need, okay? And there is one more formula for the PVRV and EPV of such a contract, and I won't do the derivation because most of the students are not liking too many derivations here. So I'm going to skip the derivation. I'm going to give you a logic for it, an intuitive logic. If you want the derivation, you can again contact me personally. You have my number. It is 918290386768. Okay. So the other formula for this type of a contract is for a present value random variable. See, the formula is that uh, it is 0 when kx is less than n. Obviously it is always that way because it is a deferred annuity and it starts after n years. For kx greater than equal to n, what we had earlier, in place of that it is a kx minus an. So all this formula is saying is that the present value of such an annuity is just of a deferred annuity is just if the payments are starting at time n and the person is aged x at the beginning. So it is saying that it is the difference of a whole life annuity starting here. So the present value of a whole life annuity starting here and payable every year, okay, minus the present value of a annuity that is starting minus this these all these payments. Okay, so the present value of all these payments would be an, and the present value of an annuity that starts at this time is akx, right? So if I deduct this part, if I deduct this part out of this whole thing, I'm just left with this part. Okay, so the payments are now beginning at time n. Okay, so that is what this formula is saying, and it is very logical. And in order to prove that this formula is same as the previous formula, I'm going to do a little proof. So the earlier formula was saying that the PVRV was just going from zero. It is zero when kx is less than n, and it is when it is greater than n, it is akx minus n into vn, right? Into kx, and I'll do this very small proof on proving these two equal. You can do this. See, this part is akx minus an, so this is just equal to 1 minus um, v to the power of kx divided by I, and the other part minus 1 minus vn over I, right? So this is what I have. This is the same thing. Okay, so if I deduct these two, it would just be 1 v to the power of n minus v to the power of kx upon I, right? That is what I will have. So this is what it is. Okay, and this one, it is a kx minus n into vn. So this is equal to 1 minus v to the power of kx minus n divided by I into Vn, right? This is what it is. So this is the same as Vn minus v to the power of kx divided by I, right? So this is what I have, and these two things are same. So there are these two formulas for the present value random variable, so you need to know this. This is another way you can write the present value random variable, and these present value random variables are asked in the exam. They feature in the exam, so they are important to know. Okay, don't ignore these. If I talk about the expected present value, there is one more formula for the expected present value, and it is a ax minus axn. Okay, so it is the difference between a whole life annuity with the deferred payments and a temporary annuity with deferred payments. So the logic behind this formula is, I'm not doing the proof, I'm just telling you the logic. If you want the proof, just contact me personally. So the logic behind this is that at time 0, the person is aged X years. Okay, so if he buys a deferred annuity with a deferred term of n years, so the payments are starting here and happening at the end of every year as long as he's alive. If he's buying this contract, a whole life annuity, the payments are happening all the time till infinity until he is alive. And if he buys a temporary annuity, the payments are happening only till time n. So if I deduct this from if I deduct this part from this entire thing, I'm left with only this part, right? So that is the logic. So it is just removing the first n payments out of a complete series of infinite payments in order to get an annuity that is deferred by a term of n years. Okay, so this is the logic that we have for this formula. Okay, and you need to remember this formula, and you need to remember the other formula. So I'm going to write both of these clearly now. So n deferred ax is equal to ax minus axn. Okay, and it is also equal to v to the power of n into npx into n deferred ax. I'm sorry, not n deferred ax. It is equal to v to the power of n npx into ax plus n. Okay, so these are the two formulas that we have, and you should remember these two formulas, and they are very useful and helpful in solving questions. Okay, let's talk about deferred annuity, deferred annuity due, okay, or a deferred annuity payable in advance. So that is the next type of contract we have. So if the annuity is payable in advance, the payments would actually, what would happen here? The payments would start, it is deferred by a period of n years and taken by a person aged X at time 0. Okay, so the payments are deferred by n years, and as soon as n years are over, the payments would start at the beginning of the years. Okay, so the first payment would take at place at time n, the second payment would take place at time n plus 1, the third one would take place at n plus 2, and so on and so forth, right? So this is what you have, and these will go on till infinity, right? So the present value random variable is obviously similar to the last type of the contract. When we are less than n, when kx is less than n, we obviously have zero payments, right? So the PVRB is zero. And if I talk about when kx is greater than equal to n, then I am having these payments starting at time n itself. Okay, so it is a due an advanced annuity, and instead of kx minus n in the previous one, I have just one more payment that is happening at time n2. Okay, so it is kx minus n plus 1. Okay, because earlier the payments were starting at time n plus 1, and now they are starting at time n itself. Okay, so earlier there were kx minus n payments, now there are kx minus n plus 1, one more payment at time n. Okay, so this is your present value random variable. And if I talk about the EPV, if I talk about the expected present value, obviously the EPV is n deferred a due x, that is the notation, and I'm not doing the derivation for this because it is very much similar to the last contract. Okay, so it is n deferred a due x, and the formula for this is obviously, as you would have expected, a due x minus a due x plus n. So all this is saying is that if I have deferred annuity, it is the difference of a whole life annuity and an annuity that was only payable for a term of n years. So I have got at time 0, this guy is x aged, and he is taking a deferred annuity for a period of infinite, right? It is a whole life deferred annuity. So there are no payments here, no payments, and there are payments only here happening at the beginning of the years. Okay, so all this is saying is that you have to deduct infinite payments, that is a whole life annuity payable at the end of the year, and what you have to deduct out of this is this temporary annuity which was payable for n years. Okay, so out of the whole thing I am deducting the first n years, so I just cross out the first n years, and what I am left with is all the payments happening after time n, and that is the deferred annuity. And the other formula is a x plus n into npx into uh, Vn. Okay, and all this is saying is that a deferred annuity is nothing but a whole life annuity starting at age x plus n, but for that to happen, the person has to survive up till n years, and also we have to discount it back to time 0. So these two factors. So this is very similar to what happened in the last part. Okay guys, so the thing is that I am thinking that this video is getting too long, and I've already given you so many proofs to work on. So I'm not gonna overload you with any more proofs here. I think you should just process whatever I've given you so far. And there is a very small part of chapter 2 and chapter 3 left, which I would make a half an hour video and discuss and end. So this is all for part 5. There is going to be one last part 6 too. That is going to be a small 20 minutes to half an hour video in which I will finish chapter number 2 and chapter number 3. Thank you. Okay. And one more thing, see, the thing is that for all the formulas we have discussed so far, we have discussed the whole life annuities, and we have got temporary annuities and whole life assurances, and temporary assurances and deferred ones. I want you to, at the end of each chapter in the core reading, there is a summary given there. Okay, there is a summary of formulas given. So I want you to go through that summary and make sure that you understand each of those each of those summaries. And I want, as we have completed major part of these chapters, I want you to try and attempt questions too. Okay, so you can try and hit the booklet one of the revision notes too, and I'm sure you'll be able to solve them. Just don't get too bugged up in the mathematics, and just start thinking the way I have taught you to think, so you won't face any problems. Definitely, I'll be doing a lot of questions from the revision notes, especially the tricky ones. I'll be concentrating on them. So that will come after we end part 6. Till then, I want you to try them by yourself, and if you get stuck up anywhere, just message me so I can, solve those questions too, which you are getting stuck up with. Okay, thank you.